Alright. Okay, first, let's discuss the first type of problem that we have. I want to make sure that we understand the basics. So let's say we had a problem like, we'll go with 7x equals, let's go with 13. We're gonna go through this problem one more time, then we're gonna ramp up the difficulty very, very quickly. Okay? So, first step.
Or I don't think he's gonna make it difficult.
Okay, first step that we have to do here, we have to take the log of both sides. Now, the reason why we're taking log is because there's no natural numbers in this particular problem. So we're just going to take the normal logarithm. And what that does using the power rule is you can drop the x out front. This is one method of doing this problem. I'll show you the other methods that we can do for the same problem. So the x would drop out front. So this would be x times log of 7. And on the other side of the equal sign, the equality symbol, we have that log of 13. And the last step to solve for x is you do the inverse operation to the other side. We would divide by log 7. We divide that over. So x equals log 13 divided by log 7. That's probably what I'm betting most people do. Straightforward, it's easy, we understand the concept. Now, I said there's another way to do these problems, right? Because if you thought about what we did last year in pre-calc, is we've learned how to take an exponential problem and do the little circle method to it. Where
That's what I would do.
which is totally fine. I mean, the circle method is the same exact concept. You would start with a base, wrap your way all the way around until you get back to the exponent again. Bless you. So this would be log of base 7 of 13 would equal the x we're trying to get to. Now, some people's calculators, you can actually type this in. You hit the log button, it'll ask for both entries. It'll ask for the base, it'll ask for If you don't have that, this number is actually written like this in the calculator. Log of the 13, and then the base would drop out the bottom and become its own log. What you're actually looking at here is a change of base formula. The base on that particular problem is log 10. So that's why they change it. It's the same problem over here. It's just how you type it. All right, questions on those two? Those are basically the two methods you can do to solve these. All right, now, let's ramp up the difficulty a little bit. Just a little bit.
I think your difficult and my difficult are a lot.
Yeah. All right.
On a scale of difficult to extremely difficult, how difficult is this difficulty?
That's what it looks like.
I'm
Okay. All right. We're going to show both methods for how to do this problem.
Oh my gosh.
Okay. In fact, I think there's like 3 ways to do this problem. All right. One method. If you want to get the exponents by itself, you could divide the 5 over first. Don't make that 15 to the x. That's not how that works. This 15 can divide over and become 3 to the x equals 2. And then you can go from there. And this problem would be just like the last one we just did, right? Where you could take the log of both sides, the x would drop out front, and then you divide the log 3 over, right? We've done that problem. You just have to get rid of the 5 first. You want to get the exponents by themselves first. Okay? That's why I divide the 5 over. Now, there's another way to do that problem. As I said, there's about 3 different ways of doing it. Here's the other way. And this is the reason why I brought this up the other day. It's called the product rule, when you multiply things in a logarithm. So, 5 times 3 to the x equals 10. You could just, right where you start, just take the logarithm of both sides. You don't have to do that whole division thing, because maybe you didn't even notice it. Or maybe you didn't know that you could divide the 5 over first. So you would just take the log of both sides. Now, inside this logarithm, there is 2 things being multiplied together. If there's any time when there's things multiplied inside a log, you are allowed to separate them into their own logarithm. So this can be separated to log of 5 plus log of 3 to the x. Now the reason why, that is the product rule for logarithms. That if they're being multiplied, that you can separate them to their own logs and it's being added together. Does that make sense? To solve this, you would move the log 5 across. I would subtract this over. So this would be log 3 to the x, log 10 minus log 5. I would just move those over. And then you can do the rest of the steps where you drop the power out front and divide. Drop the x out front, and log 10 minus log 5, all divided by log 3. Because you drop the x out front and divide by the log 3. Now, I know the log of 10 simplifies, I understand that.
Yeah.
But the idea is that, do you understand the concept of what I did there? How I separate them. Okay, now the reason why I bring this problem up, that one specifically, this rule is something you have to do. You would have to do that rule if you have natural numbers and normal logs in the same problem. So here's how I want it. Pick one of these, like where they have like multiple like things going on, like on both sides.
Pick the girthiest one, Drew.
Pick kind of a, okay. Rattle off 18.
Actually, no, that means back
Sam.
stuff going on both sides.
Okay.
Alright, 16, which
Okay.
is 10 to the x plus 3 equals 5e to the 7 minus x.
Okay, perfect. Good choice. Good choice. All right.
That's a difficult one.
Yeah. This is a serious doozy.
Wait, what did you
Oh,
say?
This is a doozy. All right.
Why can't we do this?
All right. Okay. To do this problem, number one, we have to take logs of both sides or natural logs of both sides, however you want to think of it. Either way, you're going to get down to the same answer in the long run. I believe that when the book has a problem like this, they're going to separate into natural logs because it does have an E on it. It really honestly doesn't matter if you do a log versus a natural log. The reason being is that this thing has both natural numbers and it has whole numbers, so like, it doesn't really matter which one you pick. I believe the book will refer to using the natural log. All right, so what you're going to do here is you're going to take the natural log of both sides. Just think of the natural log like a normal logarithm, because it is literally the same style. Natural log of both sides. Okay. Does everyone understand what I just did there? Natural log of both sides. Now, what you're going to do is on this one side over here, these are going to separate into their own logarithm.
Do that again.
Okay. So, since these are being multiplied, they would separate into their own logarithm. Because it's the product rule that you can separate them just like that problem I did over here. Where this would be natural log of 5 plus natural log of e to the 7 minus x. And that 7 minus x is in the power. On the other side, this is just one natural log x plus 3. Okay, are we good so far with the concept what I've done? Question?
Wouldn't the 7 minus x, wouldn't that go to 5 too?
No, it's just on the e. If they had a parenthesis around the 5, they'd put that there.
But
So
there's not, so.
they're not. Okay. Okay. Questions at all about how I separated? Okay. Next thing, I'm going to drop those powers out front because that's a power rule. Anytime you have a natural log or a log where there's something to a power, the power can drop out front. That is the same right here. This can drop out front. So you're going to do that first. So this is x plus 3, in parentheses, natural log of 10. Over here, I have the 7 minus x, and I have the natural log of e. Questions at all? All right, now this point, I know this natural log back here goes away. Natural log e is a 1. I understand that. That will literally turn out to be a 1, and I wouldn't need these parentheses here. Up here, this doesn't go away. Natural log 10 doesn't cancel out. What you're going to have to do with this natural log of 10 is distribute it into this parenthesis. That's the same, like if this didn't disappear back here, maybe this is a natural log of 3, you'd have to distribute the natural log of 3 through the parenthesis. But since that one does turn out to be the number 1, I don't really need that parenthesis anymore. Okay, questions about that? In the front, I'm going to distribute the natural log of 10. There. Distributing the natural log of 10 to the x and the plus 3. So you each get it. The last step that I have to do here is move the x's to one side of the equal sign, right? Because it's like an algebra 1 problem. You want to get the x's to one side, the whole numbers, or the natural numbers, the decimals to the other side. So doing this problem, there's a couple things that have x's, right? I have an x right here, which is a negative x, and I have an x root, or x natural log of 10. Everything else is a number, it's a digit. I'm just going to move them to the other side. So what I'm going to do first is add this x across to this side, and I'm going to take this 3 natural log of 10, and I'm going to subtract it over here. Because I want to get the x's to the left side, whole numbers are just decimals to the right side. Does that make sense? Like in algebra. So here's what I have. I have x natural log of 10. I'm going to,
That's very nice.
it's a 10. I'm going to add the x across, that's a 1x. On the other side, I have the natural log of 5 plus a 7, and I'm going to subtract the 3 natural log of 10 across. So I moved everything from the right to the left side right here.
It's gone.
Questions with how I move things around? Okay, last step here, how to solve. I'm going to factor out the common factor. On this left side, what do they have in common? X's. I'm going to factor that out. So if I factor out an x, here's what I have. I have a natural log of 10 plus 1. On this side, there's really nothing I can do. These are all very, very different. I can't even add or subtract those together. I know those are decimals and stuff, but I'm just going to leave them like that. That's the exact answers for them. And the last step is to divide that parenthesis to the other side. And that's the answer. This is the answer I'm looking for. That when I divide this over, here's what I have. Is there a question about this?
Yeah, so all we're doing,
Is you're solving for x.
we do all that just to.
All that to get
Like
x.
x and-
What x is that? Now, I know that that fraction represents a decimal. I understand that, right? Because it is a decimal.
What if I
That
type
that
it
number-
there?
If I were to plug it into both x locations, it would make the left and right side balance. They would equal each other. That's what this x is giving me. Now, what makes these really difficult? Number one, they have a lot of different x's everywhere in the problem. They have naturals and whole numbers, like they're kind of doing a mixed bag. Because I could have done this problem differently. I could have just taken a log of both sides instead of natural log. I did natural log because I saw the e. But if I just took the normal log, this 10 would have went away. So the problem might look different, but the answers will be the exact same in the long run. So that's why the book doesn't even stress which one you pick. They just say if you see a natural, do the natural log to both sides. All right, questions at all about that particular problem? Now, here's my question to you. Do you want another one of those? Because we can pick another one if you need to see one like that.
Yeah, let's do it.
No, we don't need to see that.
No? Okay.
I think so.
We'll save for tomorrow. We'll do one more tomorrow before the homework. Okay. All right. Let's go to the next ones. Drew, I'm going to have you read off one of the books, like 32-ish, 33, 34, somewhere in that ballpark. These are going to be my last 2 to 3 problems today. Now, we're going to do kind of like mock story problems. I'm going to put some data on the board, and we're going to walk through how to do logs and natural logs using these numbers. They could be exponential growth. They could be just constant growth. I think most of these are exponential. But we'll look at kind of the numbers that are involved here. Okay? They can talk about half-life and other major numbers. Okay? So that's what we're going to be looking at. Okay. All right. So Drew, fire away. We'll fix the problems as we go. Go.
100 kilograms of radioactive substance decay to 40 kilograms in 10 years.
Slow down
Okay,
by
40 kilograms in how many years?
10.
10 years.
How much will be left in 20 years?
Okay. How many kilograms will be left in 20 years? Okay, so here's the idea. This thing is decaying at a rate. It's going from 100 kilograms down to 40 in a certain time frame. So what I see here, what I have here is I have a formula that I can go off of for exponential decay or some type of decay for this thing. And the idea is they want to know how many kilograms are left in 20 years. Like what's left of this thing. Okay, I'm expecting it to be less than 40, obviously, because I went 10 years, I went from 100 down to 40. I'm expecting this number to be like a really small digit. Okay, something smaller than obviously 40 kilograms, but significantly smaller. Okay, so how to do this? I'm going to set up this first box in its own formula. That will help me figure out its decay rate. Okay, the formula that I'm using is this. The amount of the substance is equal to P, the principal amount you start with, E to the RT. It's decaying exponentially. So I'm using an E for most of these problems. Now, if you don't want to use the E formula, we had that other formula we had the other day, which was this one. It was P, it was, I think it was like an PR to the T, and it was an amount, but this rate is the rate you're trying to decay by. It was like a percent, like you're losing 10% per day. That's different than what we're doing in these problems. These are exponential decay problems. All right, so plugging these numbers in, my initial amount of substance was 100. I don't know the rate, but it took me 10 years to decay down to 40. The amount was 40 kilograms left after 10 years. Now, do you agree that the R will be a negative number? It's decaying, right?
Yeah.
So what we're going to do is we're going to solve this. I'm going to divide the 100 over first to get the exponent by itself. So this should turn out to be 0.40. I'm going to take the natural log of both sides, so that way I can get the E to drop out. The natural log of E. And this 10R will drop out front of the natural log. Well, the natural log of E will literally go away because natural log of E turns out to be a 1. Because a natural log is a log of base E to the E, so it has to be a 1. The 10R drops out front, so it's 10R times 1. And the natural log of 0.4. So your R, the rate that I'm dropping by, if it asks for, figure out a rate, the rate that it's decaying by is I divide this by 10. So whatever my rate is, it's going to be natural log of 0.40 all divided by 10. That's my rate that I'm falling by. The natural log of 0.40 will be a negative number, and it'll be divided by 10. Now, I can type that in, I can get my decimal here in a minute. What they want to know is how many kilograms will be left after 20 years. So the idea is that it's the same formula as the one I just did here. The only thing that I'm going to figure out is the amount that they want. They want to know this, they want to know that amount. If I started with 100, I had that same decay rate, which is this number, which we can type in a calculator and figure that out, but I'm going for 20 years now. I'm going for 20 years. Now, obviously you'd already probably have this decimal typed out. Times 20, you get that decimal, E to that power, and take it times 100. Now I'm going to type this in just so you can see this amount. But I'm expecting it to be less than 40 kilograms, because it took 10 years to go down to 40. In 20 years, it should be significantly less than that. So, typing this number in. The natural log of 0.40 divided by 10, this number, this digit was negative 0.09. I took that times 20. So if I took this number times 20, that's negative 1.83. So I'm going to put E to that number. E to that number, the negative 1.3 number. And then I'm going to take it times 100. And what it tells me on my calculator is exactly 16 kilograms. It's like clean 16. Like it wasn't even a decimal, it said 16. Questions with how I got that? I put e to this power. Most people will type this in wrong because they won't use as many decimal places. I want as many decimal places as my calculator would get. E to the power times 100. Questions at all about that problem? That's the answer. You want to know how many kilograms.
Oh, I see. I see what you did.
Say it's not 12.
All right, last problem here. Drew, fire away. We're gonna do one more and then we're done for the day.
Like the.
Yeah. You can pick whatever one you want.
You take rope.
That's some quality rope right there. If I had to say something.
Let me cut down it.
Fire away.
So,
Because they have their slippers.
culture of bacteria originally number 500.
This doesn't make a roll.
After 2 hours, there are 1,500 bacteria.
Okay, so
Andrew.
after 2 hours, there's 1,500 bacteria. Okay, so there's some type of growth rate there. Okay? And what's the question?
Assuming exponential growth, how many are there in 6 hours?
Okay, boom, in 6 hours. Okay, it's the almost the exact same problem we just did. So you're gonna get used to like doing these style of problems because even though this one like kilograms something, my bacteria are growing. So my E number, the rate here, is gonna be a positive number because I'm growing from like 500 to 1,500 in 2 hours. I'm gonna use that to figure out my growth rate. So my initial amount was 500. It's growing exponentially. I'm going for 2 hours. And I'm going up to 1,500. Now the beauty about these formulas, notice that I can just type in whatever time frame I want. I don't need to do years. I can go hours, I can go minutes, I can go seconds, as long as I stick with that same number for the next one. So if it suddenly went from hours to days, I'll have to switch that to hours to make sure that my formula sticks with the same. So dividing this over, I get 3 equals e to the 2r. I'm going to take the natural log of all sides. Taking the natural log of this side, the e will drop out, and then I can divide by 2. So my growth rate is a natural log of 3 divided by 2. That will be a positive number on a calculator. The final answer is taking that growth rate and now applying it for 6 hours now.
Whoa.
Figure out what's the amount. Now obviously it's going to be more than 1,500. So my initial amount was 500. My new growth rate is this, but now we're going for 6 hours. And this is going to be in the power of above. Because my rate was that number. So I can type that in. So type this in my calculator. Natural log of 3. I'm going to divide that by 2. I'm going to take that number times 6, which is, this number turns out to be 3.29. I'm going to put that in the power of e, which this turned out to be 27, and I'm going to take that times 500. So it is telling me my answer is, my amount is going to be 13,500.
Yeah.
How you putting that to the power of e?
Okay, so I type in e, right? And so for most calculators, it gives you e and a little caret, it has a parenthesis. Then I type in the natural log of 3, make sure that's closed in parentheses, divided that by 2. And then make sure that that's times 3 inside that parenthesis. Usually what I do is I figure out this decimal first on a calculator, take it times 6, and then that's the decimal right now. And I'll just put that in the power of the e. And I think it turned to be 3.295, blah, blah, blah. I just typed out a whole number there. Questions with these natural logs and logs? The thing I'm worried about is those first couple of problems we did. Can we solve for x? Can we do all that weird stuff in the basic formulas? All right, we're done for the day?
Square?
Yeah.
Square we're done with 4?
I swear.
You shouldn't class.